Hi guys, I welcome you all for the course Introduction to Manipulator Robotics. So today's session we are going to see the introduction of a robot and what are the joints of a robot and what is the difference between robot and the robotics. Okay, so let's see. First we'll see the definitions of a robot. So robot means that is a manipulator or industrial robot is composed of series of links. So this is one link, this is one link. So it is composed of series of links. Then they are connected via joint. So this is called as joint. And each joint has an actuator. So to each joint we have an actuator. So the actuator is motor and we have sensor also. Each joint has an actuator connected to it. So this is how the manipulator is defined. So this is the definition of a robot. So it consists of series of links and then the links are connected by a joint, and in each joint you have sensor, actuator and gear arrangement we have. For example, our human hand, you can the base joint is the shoulder joint, then our forearm, then you have elbow, then our the second arm, next arm, and the wrist. So the shoulder arm and the elbow and the wrist or joint, and then this shoulder is the joint, elbow is the joint, wrist is the joint. So one best example for a robot is our human hand. Okay, so basically the robot is classified like serial manipulator. Okay, then serial manipulator, then mobile robot. Okay, so serial manipulator means one end is fixed. One end is fixed, the other end is free. So this is serial manipulator. So this is one joint, this is second joint, third joint, fourth joint, and this is your wrist, or we can say end effector. So this is the last joint. Okay. So basically, this is the manipulator. This manipulator consists of links, and the links are connected by joints. And each joint you have motor, sensor, and actuator. Motor actuator, or we have gear arrangement. So we'll learn everyone in the everything in the upcoming classes. Okay. Then the actuators. The actuators are used to cause motion between successive links. One end of the manipulator is usually connected to a stable base. Another, the other end is used to deploy a tool. In that you can give a pen to write, or you can make a robot to grip something and leave it somewhere. So likewise. So these are the definitions of robot, and we'll see what is robotics. Okay, so robotics is the, I mean, you have to use a robot, not only a robot. Along with robot, you have to use the other components like sensors, controllers, software, and then all these together it forms a robotics. So robotics is the art, knowledge base, and know-how of designing, applying, and using robots in human endeavors. So we have to use this concept to do a particular task. So robots may be used in manufacturing and environment, underwater and space exploration for aiding and disabling. So we all know about the applications of robot. Generally, a robot is an interdisciplinary subject, so which involves, main thing is mechanical engineering, and for the actuation electrical engineering, and for the controller electronic engineering, and for the software computer science engineering, and then for this AI, and then we need biology and many other disciplines. Okay, but generally, why do we need robot? Because in order to reduce the production cost, in order to increase the productivity and improve the product quality, we go for automation. That one such automation is robot. Okay, so automation used to fulfill our the above requirements. Then we have a hard or flexible automation. Robotics is an example of flexible automation. Then the main thing is in in 1940, Isaac Asimov he made three laws. The first law of the robot is robot may not injure a human, or through inaction it allow human to come to harm. So it should not injure a human, and it should not hurt the human, harm the human. Second law is the robot should obey the orders given by the human beings unless such orders would conflict with the first law. And then third one is the robot must protect its own existence as long as such protection does not conflict with the first and second law. So first one is the robot should not injure the human. Second one is the robot should obey the order. And third one is the robot should protect its own existence. So whenever you make a robot, so you have to follow these rules so that the when the industry in industry, then you will get the acceptance for that robot. And these are the interdisciplinary areas. So mechanical engineering. So what's the role of mechanical engineering in robotics? So actually, kinematics, we all know that it is a motion of the uh, motion of anything. So here we can say the robot arm. So the robot arm is, so for example here, and this is one position. So this is first position. The second position is, so this is second position. So the robot has to move from here to this. So for that, the robot has to move. Okay, either I mean, or we can go for flexible link, or you can use prismatic joint to extend. Okay, so for this we need kinematics. So we should understand what is kinematics, and then so the kinematics represents only the position. It says about how position can be derived. Okay, but we don't consider the force. Okay, next one is so once we using kinematics, the robot knows the position. Okay, in order to reach this position, the robot has some angle here, also some angle, this angle. So if you give this angle, automatically the robot will move to this position to another position. For that, we need kinematics. And dynamics is, suppose once you reach the position, then if you want to grip something and move it somewhere, so the gripping, for gripping we need force. So to grip egg, to grip apple, or to grip a stone, so as a human we know how much pressure we have to give to hold it, but for the robot we have to give that intelligence. So for that we need to study the dynamics. So dynamics is study of forces and moments. And then for here we have to collect the information of the environment, because when the robot is here, okay, so it has to move from this place to, this is uh, first place, this is second place. So it has to move from this place to this place. For that, first you have to study the current place. So this is for this joint. At this joint, you have to use a sensor to measure what is the current position. So we need to collect the information of the robot joint, and also to collect the information of the environment. And is there any obstacle out there? And next comes the computer science engineering. So to plan the, suppose the robot has to follow this path. So this path can be like this path can be like this path can be like this. But you have to optimize the path with the minimal investment of energy, I mean computation, and minimal cost. So we have to make a plan. So for that we need a software. So for that we are going for computer science. And we need artificial intelligence also, because we have to impart the human intelligence to that. For that we can train the model, deep learning, machine learning, so we can use that. So we need computer science. Next one is electrical and electronics engineering for control schemes to implement the controller. So here, for example, this is the sensor. So this sensor will sense the angle is 45 degree. Okay. So if I want to make a robot to move over here, third position, so this is the angle. So you have to increase the angle, but the current angle is 45. So we need a controller. In that controller, this current angle is 45 is compared with the required angle. So required angle is 75. So the difference is 30 degree. So based on this angle, you have to give the actuation so that this this link will move to this side based on the actuation. Okay, for that we need control schemes. So for that we have to use this electrical and electronics engineering. Then general sciences. Okay, so hence we can say robotics is a interdisciplinary areas. Then what are the robot components? So first thing is the manipulator. So let us take one simple manipulator. So this is link 1, this is link 2, this is joint. In each joint you have gear arrangement, motor and sensor. Here also you have gear arrangement, motor and sensor. This is the end effector. This is your gripper. Okay, so here also you have uh, this joint, you have motor, sensor and gears. Okay, so first component is manipulator. So this is the manipulator. So this one is the manipulator. This one is the manipulator. So this is the main body of the robot. Then after that, end effector. So the end effector can be gripper. Suppose if you want to grip something and leave it somewhere, we need a gripper. Or the end effector may be tool. If you want to paint, if you want to spray, or if you want to make a hole, we need a tool. Or if you want to do welding, we need a tool. So this end effector. This end effector could be either gripper or tool based on the application. Then actuators. For each joint you have actuators. So how it works? First, the current joint position is sensed, and then that sense is given to a controller. We have a different controller. So this sensor is given to a controller, this sensor's data is given to the controller, this sensor data, and then so here this is a controller. So these are all sensors, one value, joint two value, then this is end effector value. So all these value will be taken. Inside you have set point database. So this, for example, joint one has different set point. So both are compared, and then it takes a control action, and then it says that okay, so if that voltage is given to the motor will take the voltage and will do the mechanical motion. Mechanical motion is, suppose if the robot is here, the link is here, it makes the link to move to this much angle. So that is decided by this controller output. And so we need gear because in order to reduce the speed, because this is too much, we have to reduce the speed as well as we have to increase the torque so that you can rotate the length. To reduce the speed and to increase the torque, we need a gear arrangement. So that's why we have gears in all the joints. So that's actuators. Sensor also, what is the use of the controller? So I said for each joint, it's a joint control system. We can't have one controller for all. Okay, so the logic is every joint should be controlled independently, every joint. So we have to remember this law or rule or this concept. Every joint should be controlled independently and similarly. Okay, so for that, for each joint we have a sensor and actuator and gear arrangement, but the control will take a decision and it will pass the information to each actuator to do the actuation. Then the processor is your computer, or your controller is a processor. You can use Arduino also, or you can use Raspberry Pi, any processor you can use to do the processing. And we need a software to implement that. So these are the robot components. So here it is clearly mentioned. So here this is the link, this is one link, this is another link, and then here is a joint. So the links are connected by a joint, and then at each joint you have a sensor and actuator, and then inside, if you want gear arrangement, they can use. Okay, so likewise all the informations are connected to this controller. So here is a controller, this is a controller. So we need a processor, software and the control algorithms, and then here is your wrist, this is your wrist. To that end effector is connected. So this is a gripper actually. Okay, so these are the parts of the robot. Then what are the terminologies we are going to use? So first we know that what is a manipulator. So manipulator is a robotic arm in which you have a series of links, and these links are connected by a joint and one end of the link is, or one of the joint is stable, the other end is move, it is allowed to move freely. To that end, end effector, which is gripper or tool, is connected. So that is robot manipulator. And then kinematics. So kinematics means if you give angle to the manipulator, it will give you xy coordinates. Or since it is an angle, so we can say it is joint space. If you give joint space coordinates, it will produce Cartesian space coordinates. For example, let us take this simple. Okay, so now I want to know the position. Okay, so for this, or let us take a single joint. Okay, this is single joint. This is single joint. Here we have a this gripper. Okay, so we have to find out this angle. So how do we do that? So this is xy. We all know that x is equal to, cos theta equal to x by this linked length L. Okay, and then sine theta equal to y. So this is y coordinate, this is x coordinate. So sine theta equal to y by L. So from this we can say x equal to L cos theta and y equal to L sine theta. We know the value of linked length, and theta also know, we know. So this point, this is called as joint space, and then this is called as Cartesian space. Okay, so when you give the angle, if you give the angle, automatically your x coordinates will be evaluated. So using the angle, if we will be able to evaluate the coordinates, then that is called as direct kinematics, because we give the angle and then we give when the actuator will give that angle, accordingly your robot move from one place to another place. So it involves motion. So that is the position. It moves from one to that. And if you want, we can take a derivative and find out the velocity also. So this concept is called as direct kinematics, in which when you give the angle, it give the it will give you the Cartesian coordinates x and y. Okay, so that is called as direct kinematics. Then inverse kinematics is just opposite. Suppose if I know the location already, I want the robot to be here, or after some time I want the robot to be here. So in this case, your Cartesian, I mean the xy position, so for example, 4 comma 8.3 centimeter, or 3 comma 10.6. So this informations are known to you. So when you give this information, your inverse kinematics will find out the theta. Okay. So your if Cartesian, if you do the actuation, or if you do the task with respect to Cartesian space, means that is called as inverse kinematic. That is, we know the xy coordinates value. From that, you have to determine the angle using controller or using inverse kinematics. That then we have to use the actuator to move towards that angle. So this is called as inverse kinematics. Okay, so we know it direct kinematics and inverse kinematics. Then from this we have to do the trajectory planning. So we have to do trajectory planning is either do you want to do the trajectory planning at joint space, or do you want to do it at the Cartesian space. That also you have to decide. So trajectory means you have to say that this is the start point, this is the goal point, and you have to say how much velocity your manipulator should move. So that information will be given by this trajectory planning. Okay. Then after that, you have differential motion and statics, because differential motion in the sense velocity. So we have to check what is the Jacobian. So Jacobian we always use, you know why? Because the Jacobian will say, suppose if this is the robot, so it says on which area the robot is free to move, on which areas it cannot move. So that information is given by Jacobian. Okay. Then static is force is involved. Then manipulator dynamics, because once we make the robot to reach a particular position, then if there is a object to be gripped, so we need to know the force. So that force information will be given by manipulator dynamics. Then robotics vision. Okay, for certain things, or even though we have sensors, we should use a camera to know the location, to read the location. From that location also we'll be able to make a robot to move from one place to another place. Then task planning. Okay, so once you once the task is verified, only we have to move for it. So what task it is, so you have to plan the task. Then finally robot control, because you have to control the robot to make the robot to move on a specified trajectory. So these are the terminologies we use in robot. Then we'll see the classification based on application. So these are all known to you, not a new thing. So we know that the first one is industrial robots. For that only they have made a robot. So you can see these are all serial manipulator. So it is fixed at the base. Here also one more robot that is fixed at the base. See, you can see this end is free. So here you can see this is joint number 1, joint number 2, joint number 3, and then joint number 4. Okay, so likewise the number of joints is serial, and then each joint you have sensor, actuator, and gear arrangement. And then at a time, because you have to program the robot. So according to the program, it does the action. After time, we can see one, two, three, four cars in the lane. So we have four robots. So one robot this side, another robot, another four. So totally eight robots to serve the car. Serve the car in the sense, so it will try to fix the door, or it will try to paint it, or it will try to make a hole, or it will try to fix the seat, because this is, I can say, symmetrical. So whatever action you do, the same thing should be repeated this side also. For that we have robot. So this is one application, industrial robot classification. Next one is domestic. We all know that to clean we can use a robots to do that. Then surgical robots, that is, suppose if it is a bot. In this bot you can inject this medicine and make a robot to move. So the robot will move, and then when it reaches the cancer affected areas, it's just uh, pass the medicine. So in that way it is cleared. This is surgical robots. Or suppose this is a knee. So in this, I need to make a hole on the knee. For that, I can use a serial manipulator. So you can direct the robot to make a hole. For to make a hole, here we have to give a tool. Okay, the tool which makes a hole in it. That is a surgical robot. Then classification based on, yeah, because it's still continuing. Robonauts. It's, that it is. Yeah, one such is the rover, and previously we have checked that also in the Chandrayaan 1. So that is one robot, that is robot in commercial entertainment. So nowadays in big metropolitan cities, you have a robot for entertainment purpose. So by seeing this, the children will be enjoying. So it give them the more income. Okay, so entertainment or talking robot. Okay, then army robots. So this is a humanoid robot. So this is one serial manipulator. This is one serial manipulator, and serial manipulator. Okay, this is also. So here one end is fixed. Then these are all link. These are all link. These are all link. Then joins. So once you make one thing, then you have to check whether it is under control. This also. So this is called as. So this is for me available, because we can have some this bomb also to make a robot to throw the bomb. So for defense purpose, we can use army robots. Okay. And the next one is service robots. It is always in the university, and it is in the R&D to implement new features. And then if you want to give the new ideas to the public, then you can use service robots. Okay. Then those are the applications of robots. Then we'll enter into the joints, because we have learned links, then we know the terminology. So next one is the joint. There are different types of joint. One is linear joint, rotary, sliding, or spherical. The most commonly used joint is linear. So if it is a, then you have to make use a joint, so which will actuate the link to move in one particular direction. So the degree of freedom, we used to say it is one. Okay, for example, this is the revolute joint. So if you give the actuation, this joint will move like this, will move like this. So it moves, or it rotates in only one direction. So it is free to rotate only in one direction. So it has got the degree of freedom as one. Degree of freedom means it says in what direction it is allowed to move freely. Okay, so here is your prismatic joint. So this link, this will move up and down. So here it rotates, so that is why it is a rotary joint, or revolute. It moves up and down. So this is prismatic joint. Here also it moves either this direction or this direction. So it has got the degree of freedom as one, because degree of freedom means in which direction it is free to move. So it is free to move in this direction. So its degree of freedom is one. Okay. Then you can see this ball and socket, our spherical, or shoulder joint is like this. So spherical joint, which means it can be rotated like this, or it can be rotated in all three directions. The axis of rotation is in all three directions. So it has a more flexibility. You can check with your human arm. Okay, the shoulder joint. So since it, because we have only the maximum one is three dimension, XY direction. So it has got the degree of freedom as three, because it can rotate in X direction, Y direction, and Z direction. Okay. And then next one is hook joint. So it has got 2 degrees of freedom, because this is hook. So here, so This can move like this can move like this. So we have here one direction, here one, totally 2 degrees of freedom. Okay, then next on the cylindrical joint, so you have the variable here as well as you have the variable. So 2 degree joint. So we have prismatic as well as rotary joint. Okay, and then this is one twisted joint. You can twist in this fashion. Okay, so these are the variable joints used in the robot. Then we'll discuss the characteristics. So what are the characteristics of the robot? Then so when you make a robot, you have to make sure that your robot should follow this characteristic, or this will be useful in preparing a data sheet. So by seeing the data sheet, we can understand that whether this robot is suitable for our purpose. So in that, first one is payload. Okay, so first one is payload. Okay, so payload is, for example, in this payload, you have to consider the robot weight, the complete robot weight, because robot weight is, even if you take one simple link, for each joint you have a gear, motor and sensor. Just imagine how much is the robot weight. So always the robot weight is too much than the weight it can carry. For example, if the weight of the robot is 86, then the payload must be 6.6. Similarly, when the weight of the robot is 594, the weight of the object to be carried by the robot is 35 lb. So to that extent, so we have to first give the limit how much load is it can carry. So that is payload. So when you check the data sheet, so in the data sheet, the first thing is payload. By seeing the weight, then you can check whether it will suit your um, project or it will suit your need. Okay. Then the reach. So reach is the, actually for this we should know what is work envelope. What is work envelope, or we can say workspace. Okay, for this we all can try our human hand. Okay, so all of you can stretch your human hand and take it up and just try. I mean, use that hand and make a. Use the hand to move in some direction. If you stand, if you sit in, if you sit and move your hand, you can make one semicircle. So the workspace of the human hand at sitting poses semicircle. Only within the circle you can reach. I cannot reach the ceiling. Okay, I cannot reach the fan, okay, which is above me. I cannot reach the table which is above me. Okay, so workspaces, it is the maximum distance that can be reached by the end effector, not only the last one, not the whole thing. So you should know the reach also. So that suppose if your reach is, so here is the, here is the link, here is the link. So this robot can move like this. Okay, suppose if this is welded, then it cannot. So it can reach only this area. So your task should be kept in this area. If you keep the task here, the robot cannot move. Okay. So while you sit, will you be able to reach the ceiling? No, because your maximum reaches only a particular distance. So that reach you should know. Then only you can check whether this robot suits your need or not. Okay. So that is your reach. So here the robot may be reached with any desired, not only one. If it is more than one, then that is called as dexterous space. Then non-dexterous means at least one time, only once it can reach. So while you make a robot or while you buy a robot, you have to see this important characteristic, reach. Next one is precision. The reason for using the robot is to do a particular task repeatedly. For example, here is a robot. So this is the manipulator. So this has to move here, and then this has to move here. This is the pusher. So this here and here, because it wants to make a hole, then it has to make a hole. So it has to repeat the task 1 lakh time, for example. The human being are very tired, so tired, but the robot is not. So it will do the repeated task only, because the robot cost is more. So if you buy a robot, so make sure that the robot, I mean, you're using the robot to do a particular task many number of times. So in order, so while doing that thing, so you have to the precision has to be maintained, because every time it moves, every time it moves from here to here, so it should reach only this point. It should not reach this point, or it should not reach this point, or it should not reach this point. So every time when it reaches the particular area, it has to reach the point precisely. For example, if you give like 4.04 is your target, so every time you repeat the same task, it should be like this 4.04, which means highly precise. Okay, if it is 4.1 or sometimes 4.04, sometimes 4.6, sometimes 4.1, likewise means, so this is the precision is very very poor. Okay, so precision is very very important. Then repeatability, so how long you are going to repeat the task, so that repeatability is also very very important. Okay, suppose if you use a robot to make to do the knee surgery, suppose for example if you want to make a hole here, okay, because of this issue, uh, so instead of making a hole, if you make a hole here, definitely the other tissues will be, will be damaged. So we need highly precise value for this. Okay, so that is called as repeatability. So with this, we can make a data sheet for a robot. The first thing is, what is the payload? So this is data sheet. So robot data sheet. Suppose if you make a robot, so you can write your name. Okay, so my name is Vimala. So Vimala robot data sheet. Likewise, you can make a sheet. So that first thing is payload. Second one is what's the maximum reach, or we can say workspace. Okay, what is the maximum reach can, and precise, precision, how much percentage, and then fourth one is repeatability. Okay, so that when a task is repeated, how fast it is repeating, or what is the accuracy for that. So you have to verify that repeatability. And apart from that, we should know the degree of freedom. What is the degree of freedom? So in what direction it can move, in what direction it is free to move. So that is degree of freedom. Then you can say about what are the actuators you are using at the joint, what sensor you are going to use it, and the gear arrangement, the gear mechanism. So you have to mention the mechanism of the arm. So like where these are the data sheet contents. Okay. Then based on the robot coordinate, we have some classifications. Okay, the function of a robot major joints is to reach a designated point in space. To do this, the robot can be designed to move with linear motion or angular motion or combination of linear angles. Okay, so first the first coordinate is Cartesian coordinates. You can see here. See, this can move like this, and then here one link. So that link can move like this. So this one can move like this. So it moves in all three directions. So the degree of freedom is 3 half. And then all the joints are prismatic. So we can see 3p or PPP, because this is prismatic, this is prismatic, this is prismatic means linear moment. So this configuration is 3p robot, or the other name is Cartesian robot. Okay. Okay. So here three linear prismatic joints to deliver linear motion only. Okay, and then this is for extensive, for horizontal travel, such as gantry robot, or for stacking parts of it. And it is easy to program. It has got highest repeatability, and with larger robots, it has got very good payload. Okay, so for every robot, you should remember this. Then accordingly choose the coordinates, that's the particular coordinate, I mean the manipulator. So next one is the cylindrical robot. So here the base joint will move like this. So you have one rotary, and then it moves this direction. You have one prismatic, another one is also prismatic. Since it moves, I mean it can rotate and moves this fashion and this fashion, then that is called as RPP manipulator. Okay. For example, you take a boat. Okay, so here I have written something. I have written something. I have written something. So I have to use a duster. That duster should run, but this duster should work autonomously. Okay, for that purpose, so first you assume the duster should move this direction, y direction. So 1 degree of freedom. Then you can, if you use only in this direction, only this portion will be erased. but this portion will not be erased. So you make a robot to move in this direction also. So one more degree of freedom, which is in this is y direction, this is in x direction. Then in order to have more flexibility, we allow this duster to move in this fashion through some rotation. So here is this is your axis of rotation. Okay. So when you do that, then you have one more degree of freedom. So totally 3 degree of freedom, which is one revolute. So you have one revolute and then two prismatic. So you can use this kind of robot to rub the board. So this is one example for cylindrical. Okay, so one revolute and two prismatic. And then next one is spherical. In this, see one revolute, one more revolute. This one. So if you do like this, so this is axis of rotation. Okay, so this one will move like this and like this. And then if it is like this, it moves in this fashion. Then if it is like this, it moves in this fashion. So first joint is rotary joint, and then the second one is moving this way. So second joint is prismatic joint. Sorry, second joint is rotary because it's rotating. Second joint is rotary joint, and third joint is prismatic. So the configuration is rotary, rotary, revolute, revolute, and prismatic. Okay. So this manipulator is called as spherical manipulator. Okay. Next one is revolute. The revolute robot means all rotational joints, all are rotational joints, and it's more flexible. Okay, so here this, it rotates in this way, this rotation this way, this rotates this way. This is, so if all are rotate, all are under rotation in all directions, then that is called as revolute coordinate system. So two disadvantages for this revolute robot are the reduction in load carrying ability. Okay, when the arm is at the end of its reach capability, and the advanced computer control capability required for both coordinate system and the need for articulated motion. Okay, so here there is a reduction in the load carrying ability. This is your revolute coordinate system. So you can see this is revolute, and this is also revolute. This is also revolute. So three are okay. Then wrist coordinate system. So in the wrist is attached to the end of the arm. End effector is attached to the wrist assembly. The function of wrist assembly is to orient. So you have to orient. You have to make a robot to orient to rotate. Then the body arm determines the global position of the end effector. So next one is each robot has its own strong points. The Cartesian has the best repeatability because we have strong points for each robot. The first robot we have studied is rectangular manipulator or Cartesian robot. In this, the best repeatability, and it is easy, simple. It is easy to program. Second one is the cylindrical robot. In this, somewhat easy to program compared to this, but offer a good lift capability. Okay, because the Cartesian will move this way, and this way. So it cannot lift. But since this cylindrical robot has one flexibility, it moves in this direction, it picks and places. Both the spherical and revolute robots excel in arm extension and flexibility. So whenever you compare these two has got more flexibility. Then the revolute robot mimic our human arm motion fairly well, and thus it can be taught in certain tests like paint spraying.